Good morning, students. In today's lecture, we will continue Wedderburn-Artin Theorem. Let me remind you the statement of theorem. If R is left Artinian ring with unity and no non-zero nilpotent ideals, then R is isomorphic to a finite direct sum of matrix rings over division rings. The proof of this theorem we had started yesterday, and in the first step we have proved every non-zero left ideal of the ring R is generated by an idempotent. Now I will continue the remaining part of this theorem from here. Now let us take F, which is the collection of all the non-zero minimal left ideals of the ring R. These ideals I have denoted by I lambda, where lambda belongs to the family of indexes. This F we have taken as the family of all non-zero minimal left ideals of the ring R. Now because we are given the ring R is left Artinian, so this family will be non-empty family. Let us take I is the sum of the members from this family F. So we can write I is equal to summation I lambda, where lambda belongs to index set. Now sum of left ideals of ring R is again a left ideal of R. So we can say that I is non-zero left ideal of the ring R. Now in the first step we have proved that every non-zero left ideal of R is generated by an idempotent. So we can say that I will be generated by an idempotent. So there exists an idempotent, say E, belonging to I, such that I is generated by E. Means I can be written as R into E. Now we claim that this idempotent is the unity element of the ring R. Unity element of the ring R we have denoted by 1. So we claim that E is equal to 1. We prove it by contradiction. Let if possible E is not equal to the unity of the ring R. So 1 minus E, that is non-zero, and therefore we can say that R into 1 minus E is non-zero. Now we are given R is left Artinian. Therefore there will exist a minimal left ideal, say J, of the ring R, which will be contained in R into 1 minus E. Now because J is minimal left ideal of R, and the collection of all the minimal left ideals of R we have taken as F, so J belongs to F, and therefore we can say that J is contained in I, because I is the sum of all the minimal left ideals of the ring R which are in the family F. So J is contained in I, and I is R into E. So we can say that J is contained in RE. Now from here J is contained in R into 1 minus E. So we can say that J is contained in their intersection. So we have obtained J is contained in the intersection of RE and R into 1 minus E. In the first step we have proved that this intersection is zero ideal. So from here we have obtained J is zero ideal, which is a contradiction. So this contradiction proves that our assumption is wrong. Means the idempotent E is the unity element of the ring R. Now because I is equal to RE and E is 1, so we can say that I is equal to R. Now I is the sum of all the minimal left ideals of the ring R. So we can say that R is summation I lambda, where lambda belongs to index set. Here each I lambda is non-zero minimal left ideal of ring R. Now, because the minimal left ideals of R that are simple sum modules of R, so we can say that each I lambda in this sum, that is a simple ideal, and R being the sum of simple sum modules will become semi-simple. So we can say that R is semi-simple. Now let me remind you the theorem which we discussed in the previous section. We will use that theorem here. According to this theorem, if M is the sum of simple R sum modules M alpha, then there exists a subset lambda dash of lambda such that M can be written as the direct sum of the members M alpha, where alpha belongs to this subset lambda dash. So we can use this result here because here R is semi-simple. So there will exist a subset of the set lambda such that R can be written as the direct sum of I lambdas, where lambda belongs to lambda dash. Now, because the ring R has unity element and R is the direct sum of I lambdas, so we can write 1 is equal to E lambda 1 plus E lambda 2 plus E lambda 3 and so on up to E lambda n. Here, these E lambda i's, they belongs to I lambda I, and these lambda i's, they belongs to the subset lambda dash. Now, for an element R belonging to the ring R, R can be written as R into unity. Putting the value of unity from here, this can be written as R is equal to R into E lambda 1 plus R into E lambda 2 plus R into E lambda 3 and so on. Last is R into E lambda n. Now, this element belongs to I lambda 1, this element belongs to I lambda 2, and this element belongs to I lambda n. So, we can say that R belongs to I lambda 1 plus I lambda 2 plus I lambda 3 and so on up to I lambda n. So, we have proved R is contained in the sum I lambda 1 plus I lambda 2 plus I lambda 3 and so on up to I lambda n. And this sum is further contained in R because all these are the minimal left ideals of the ring R. So we have proved R is the sum of the ideals I lambda 1, I lambda 2, I lambda 3 up to I lambda n. Here R is semi-simple, so we can write this sum as direct sum. Now the elements E lambda I, they belongs to I lambda I. So R into E lambda I, that will be contained in I lambda I, and these I lambda i's, these are the minimal left ideals of the ring R. So by definition of minimal left ideal, if the ideal R E lambda I is contained in I lambda I, then they must be same. So we can say that the ideals I lambda I will be same as the ideals R E lambda i's by definition of minimal left ideal of the ring R. So we can put I lambda 1 as R E lambda 1, I lambda 2 as R E lambda 2, I lambda n as R E lambda n. So we have proved R can be written as the direct sum of the ideals R E lambda 1, R E lambda 2 and so on up to R E lambda n. For our convenience, let us do the re-indexing. So after re-indexing, we can write these suffixes replacing by 1, 2, 3 and so on for our convenience. So R can be written as RE1, direct sum RE2, direct sum RE3 and so on. Last we have taken REN. So R is the direct sum of minimal left ideals. Now in this family of minimal left ideals RE1, RE2, RE3 up to REN, let us choose the largest subfamily consisting of all the minimal left ideals which are not isomorphic to each other as left R modules. So let us take this subfamily B, RE1, RE2, RE3 and so on up to REK. So in these subfamilies, the members are not isomorphic to each other. Now let us take the number of left ideals in the family REI that are isomorphic to REI is Ni. Means in the family RE1, the number of left ideals which are isomorphic to RE1, that is N1. The number of left ideals in the family RE2 which are isomorphic to RE2, that is N2, and so on. So we can write R is equal to RE1 direct sum. So we have taken N1 summons in the first bracket, means RE1, the sub-ideals which are isomorphic to RE1. Then in the second bracket we have taken N2 summons. In this bracket all the ideals, they are isomorphic to each other, and continuing like this, in the last bracket we have Nk summons. Here each set of brackets contains pairwise isomorphic minimal left ideals. No minimal left ideal in any pair of bracket is isomorphic to the minimal left ideal in another bracket. Means if we take a minimal left ideal from this bracket, that will be my isomorphic to ideal within this bracket. That will not be isomorphic to any member from any of the other brackets. So we can say that the ring of homomorphisms from REI into REJ, that will be 0 whenever I and J will be different, because the minimal left ideals in the different brackets are not isomorphic to each other. And whenever I and J will be same, then the ring of homomorphisms from REI into itself, that will be a division ring by using Sker's lemma. We have denoted this division ring by Di. Now let me remind you the result which we done in the starting of this section. For the modules M1, M2, M3 up to Mn, if M is the direct sum of these modules, then the ring of homomorphisms of module M into itself, that is isomorphic to the matrix ring of n cross n matrices having this form Fij. Here Fij belongs to Aij. Aij is the set of all the homomorphisms from module Mj into the module Mi. So we can use this result here. So using this result here, we can write the ring of endomorphisms of R, that is isomorphic to the matrix ring in which the first block, that is of n1 order, here A11, that can be written as by writing D1, D1, D1. This is a block of n1 order. Second A22, that will be a block of order n2. We have written by D2, D2 for this. And the last block, that is of order nk, which is we have denoted by writing all the elements as decays. Now this block, which is of n1 order, we have written it as D1 n1. Second block, which is of n2 order, we have denoted by D2 n2, and the last one we have denoted by dk nk. So we have proved the ring of homomorphisms of R into itself is isomorphic to this direct sum of the matrix rings. Now we have already discussed that the ring of endomorphisms of the ring R regarded as left R module, that is isomorphic to the opposite ring of R. Now because this is isomorphic to opposite ring of R as rings, and this ring is also isomorphic to the direct sum of matrix rings, so we can say that the opposite ring of R is isomorphic to the direct sum of D1 n1, D2 n2, up to dknk. Now let us take opposite on both sides. So this will become the opposite of the opposite ring of R, that is isomorphic to, here taking opposites, this will become d1n1, its opposite, direct sum d2n2, its opposite, and so on. Now opposite ring of a division ring, that is again a division ring, and also this ring is isomorphic to the ring d1 opposite n1. This ring is isomorphic to the ring d2 opposite n2, because if we define the mapping phi from d opposite n into the ring dn opposite, then this is an isomorphism of matrix rings. So from here we can say that ring R is isomorphic to the finite direct sum of the matrix rings over the division rings. So this completes the proof of Wedderburn-Artin theorem.